Hello, colleague. We will get started at 10 a.m. DC time. I'm Mercedes. Could you do me a favor, Mercedes? Hold on. Okay. If you unmute
My
yourself.
microphone, yeah. Is it working now?
It is working now, yes.
Excellent, thank you.
Could you spotlight me, so that means if you go to the bottom right-hand corner of my picture, there are 3 dots.
Yeah.
And click Add Spotlight.
Yeah.
Please. And Xiao
Add a
Zhao, I will
spotlight.
spotlight you.
Okay.
Yeah, please.
Spotlight for everyone. No. Did I put
not
spotlight?
everyone.
How do I change that?
Let's see.
Stop spotlighting. Okay.
Okay.
We have to do it again. Sorry.
Yes, just the 3 dots and
Yeah.
then add spotlight. Actually, it looks like I can add myself.
John. Okay.
The spotlight
Yeah.
for everyone. Okay. Yeah. And when Virginia comes in, I'll spotlight her, and then Xiao Zhao, I'll add you when you're going to be speaking, okay? We have 1 colleague in the room already.
Great. Early
We'll
bird.
get started. Yes. Get started at 10 a.m. And you can put your slides up if you want, Mercedes, when you're ready.
All right.
Hi, Virginia.
Yeah. Does it show?
Hello. Yes, looks good.
Okay.
Thoko, let us know where you're joining us from today if you have access to the chat, which you should.
Xiao Xiao.
Go ahead.
Feel free if there are technical questions in the chat. If you want to answer them in written, feel free to do that. Thank you. Is that okay, Joanna? Sorry, I should have.
Absolutely. Absolutely.
Yeah.
It sounds perfect. And today we have, for participants, we have cameras on. People can turn cameras on, but audio off. So the only people with audio
So all
on
the
would be
questions
our
are in
speakers.
written?
That's correct. In chat.
Okay. All right. Chat. Perfect. I last checked this morning, and we have 176
Fantastic.
participants, at least that they're registered.
That's fantastic. Excellent.
Wow. It's exciting. Yeah.
That's a great number. And you said from all over the globe, which is fantastic. Just
there were so many countries in the list. My goodness.
Welcome, Sonia. Please feel free to post from where you're joining in the chat today. We'll get started at 10 a.m., just a couple minutes. Some more people coming in. Welcome, colleagues, to today's global session. We will get started in a couple of minutes at 10 a.m. DC time. And while you're joining, please feel free to post in the chat where you're joining from today.
Wow. Rome,
Hope it's a
beautiful.
lovely
I
day in
used to
Rome.
live in Rome. Love it.
Barcelona, lovely places.
Wow.
Thanks for joining us today. Notre Dame, my alma mater.
Mm. Wow. That I never been, so another place to visit to put on my list.
We have some more people joining. We'll just wait a couple minutes and get started at about 10 a.m. Welcome, colleagues. Please feel free to post in the chat from where you're joining today. We have a truly global event and excited to get started in just a couple minutes. We'll just wait for a few more people to join. And as you're joining, please feel free to post in chat where you are from. I'd love to see locations everyone's joining from today. Washington, D.C., that's where we are. Your speakers today are joining from as well. So I'm going to go ahead and get started as you are posting in chat your location. So welcome to today's Global Evaluation Week event on AI in Action, Human in the Loop Evaluation for Rigorous Insights. And we hope you've been enjoying this week of knowledge sharing with GEI. And as I have been saying, please post in chat where you're joining us from, and we will go ahead and get started. We're thrilled to bring you work from the World Bank Group's Independent Evaluation Group, IEG. And IEG evaluates the development effectiveness of World Bank Group projects and provides evaluative evidence to support the bank group in delivering improved services and results to clients by generating lessons from past experiences and promoting accountability to shareholders and stakeholders. And our session today explores two practical AI applications in evaluation through a human in the loop lens, embedding AI across the data analytics phase. So the first case demonstrates classifying project documents into interventions using a predefined taxonomy via a 5-stage pipeline. And the second segment expands the perspective by introducing geospatial AI as a complementary set of applications for generating evaluative evidence from spatial data. And we'll follow this with a Q&A session. We welcome you to post your comments and questions in chat at any time. And for our speakers today, it's my pleasure to introduce Mercedes Velez. She is a Senior Evaluation Officer at IEG, leading the design of complex, multi-level mixed methods evaluations across human development with innovative AI-enabled approaches. And secondly, we have Virginia Ziulu. She's a data scientist at IEG, and her work focuses on the application of complex geospatial methods in the context of IEG evaluations. So again, please feel free to post questions and comments. We will get to those after the two presentations. And now I'll hand over to Mercedes.
Thank you, Joanna, and thank you all for joining to our local session today, especially given the more than 300 events that are taking place this year. So thank you so much for joining. Well, looking at the chat, as we were saying, it is wonderful to see so many countries people are joining from. Today, as Joanna was saying, I will share our experience using generative AI for text classification. And more importantly, we will show you how we designed a workflow that allow AI to become a trusted tool for evaluation. I'm also joined today by one of our data analysts, Xiao, who was deeply involved in all the implementation process, and she was really had the day-to-day interactions with AI throughout the evaluation. So let me start providing you some context for the evaluation challenge we were trying to solve. Around April last year, we were conducting this evaluation of the World Bank support to pandemic preparedness. It is a standard for our work. One of our core methods was portfolio review, supported by content analysis. To answer our evaluation questions regarding relevance and effectiveness, we first needed to clearly understand what type of interventions the World Bank was actually financing. So, for example, which pandemic preparedness capacities received most investments, or where were the gaps? And most importantly, whether these investments were aligned with country needs and capacity gaps. So without a classification of interventions, we could simply not answer these questions. A common challenge in thematic evaluations is how to classify this large project portfolio into clear categories, groups, or thematic areas. In our case, the evaluation covered more than 25 years of World Bank support across many sectors, including health, agriculture, environment, and private sector investments. And this resulted in more than 1,300 projects that require reviewing large amount and thousands of pages of project documents. So we needed to go beyond project titles and higher level objectives and really extract and analyze specific activities that were financed by each project. So we had different options. We evaluated different options how to do this. And of course, traditionally in this classification work was rely on manual coding, that is going document by document, extracting interventions and tagging them according to a taxonomy. But with this scale, that would have become extremely time consuming for us. We also consider using supervised machine learning, which we had used in the past in other evaluations. But again, this was not also a straightforward option for us because the taxonomy was quite large, included many disaggregated and nuanced interventions, around 50, and we did not have a pre-labeled data training set, manually coded training set to train the model. So we decided to innovate, and here is when generative AI entered the evaluation. But at the same time, we did not want it like a black box AI solution. So the question became for us, how do we use generative AI in a way that remains rigorous enough for us? Or in other words, can AI classify text in a way that we evaluators can trust? So unlike our experience with supervised machine learning, here there's now a widely established framework to validate and apply large language models to complex portfolio classification. So instead of building it from scratch, we built on what we already knew, right? And we drew on principles from supervised machine learning and designed a structured workflow for generative AI. Inside the team, we call it the AI roadmap. And what this roadmap look like? So this is our roadmap, and it is built around one simple principle, which is human in the loop at every stage. Humans, we were involved in every stage, in defining the methodology, in developing and testing the prompts, in validating the model performance, in refining the classifications, and also at the later stage in designing a quality assurance checks. So human coded data serve as the ground truth against which we benchmark performance, and we tested the AI outputs and also guided improvements throughout the process. This was not a linear, one-way automated pipeline. It was actually an iterative workflow in which it was designed specifically as a two-way. And this two-way road actually represents our ability to go back whenever needed and change things. So each stage is represented by a roundabout because we can make a U-turn and go back. If the taxonomy was unclear, we went back and refined it. If the validation revealed weak performance, we adjusted the prompts and rerun the classification. But in practice, this roadmap, it was applied, often run in parallel. That means that we move simultaneously. While I was developing part of the taxonomy, the analyst was preparing the data set and testing some other part of the taxonomy, and then I review the outputs of that taxonomy and then go back and change it. So we work in blocks because the taxonomy allow us, because they have 9 groups, to work each group at different times. So this was never about AI replacing us, the evaluator. It was about embedding AI in an iterative process driven by human expertise, judgment, and oversight. And this roadmap became the foundation of the 5-stage workflow that I will walk you through in the next slide. So everything started with the taxonomy. Before using AI, we needed to define what pandemic preparedness intervention actually looked like in project operations. And we developed this taxonomy inductively, in an inductive way, using 5 sources. We had conducted a scoping review of One Health interventions. We also use international health regulation frameworks. We also piloted some projects to review and learn about the context of the text and the language. And we also use a literature review of indicators that we also did, and of course, the evaluation conceptual framework. So this process resulted in, as I said, 50 interventions grouped in 9 thematic areas. And for each intervention, we develop a label and a detailed definition. The label would say, for instance, animal health and welfare, and the description would say this entailed investments in veterinary services, disease prevention and control, livestock management, etc., etc. This level of specificity of what the intervention entailed was actually critical, because these definitions ultimately became the instructions to guide the AI classification decisions. This stage basically rely on human expertise and the subject matter expert and inductive reasoning, not very much AI at this point. In the second stage, which was the LLM classification, we found that the quality of the input text was a key element. So the first decision was to identify which part of the project documents were more likely to contain descriptions of these interventions, and that was the project components. A second decision involves the length of that text. If the text was too short, it wouldn't have enough context and for the AI to understand the meaning. And if it was too much, maybe it would increase overprediction. So we experimented with different chunk size from 1-sentence level, 3-sentence level, and we ended at 8-sentence levels, mostly because of processing times. Well, I will talk about that a little bit later. We also compared different large language models that were available at the time. Think about, I'm talking about April 2025. That was Google, and then we switched to GPT 4.8. That was the final one that we used around August last year. And this was based on the results of the performance testing that we did. And in terms of the structure of the prompt, for each text chunk and every intervention subcategory, we have a prompt that contains basically 4 elements. And this, of course, I'm talking to you about the latest version that we have been refining during this process, but at the end it contained like a system instruction providing context. For example, you are a classifier in the context of the World Bank Group support to pandemic, classify whether the following text with this instruction, then the name and the definition of the intervention. A few short examples designed to distinguish among conceptually similar labels, and the chunk of the text itself. In return, the model gave us a yes or no, a binary decision, whether this text was about this intervention, and a short explanation describing how the AI reached that judgment. In stage 3, this was the human validation and assessing performance. So here we tested the models against human-coded data. So to do this, we built a validation sample of projects that they were intentionally selected because they were rich in preparedness content regarding that specific group of interventions, for instance, surveillance. So these were projects very intense in surveillance. So the idea was that we have enough positive examples across these interventions categories. So our team, human coders, we reviewed and produced a benchmark data set. At the end, this benchmark data set contained more than 14,000 chunks of text, if we consider them as 3-sentence levels, or 4,500 chunk text of 8 levels. So it was a lot of manual coding. But this enabled us to use the metrics that were commonly used in supervised machine learning to test the AI model. So we calculated accuracy, precision, recall, and F1 scores. And these are the final. The results were quite encouraging. An accuracy of 85% across all labels. Now this is average. 64% precision, 85% recall, and F1 score of 72%. A key choice, and this involved a lot of discussions with the team, and Xiao may laugh about this, was about, okay, what we prioritize, recall, accuracy, precision, and so forth. And we end up with prioritizing recall over precision. Why? Because for our evaluation purposes, missing a relevant intervention was more problematic than identifying an extra one. So a false negative means that a real preparedness capacity is not captured in the analysis, leading to systematic underestimation of what actually the World Bank is supporting. We did not want that. By contrast, if we focus on false positives, we can identify later on, as we did in stage 5, and corrected those false positives. So in that sense, our objective was to first find as many interventions as possible, knowing that we will refine them later. And going to stage 4, in which we learn from our performance metrics and refine the prompt, refine the taxonomy. So unlike supervised machine learning, in which you fine-tune the model, here we fine-tune the prompt, because the prompt has everything. It has the intervention category, the definition, and also the task description, how we describe the task. So we make different refinement. For instance, as I said, intervention definitions, we learn very quickly at the beginning that, for instance, replacing medical countermeasures in the definition for what exactly means, like vaccine, drugs, medical devices, protective, was better. It performed better. So we make those type of adjustments. Also, we make adjustment in the structure framing. For instance, subtle words changes really matter. Instead of asking, is this text related to this intervention, we use, is this text described? So changing related to describe make a huge difference. Also, we included few shots boundary examples to help the AI set boundaries, what is in and out. And as I said before, we tested different chunk text. So after each adjustment, we rerun the classification and comparing results with the human coded benchmark sample. And we repeated the process. And of course, we focus on those interventions that had the lower metrics. For instance, some interventions performed very well from the beginning and we did not touch them. But for others, we have to do several rounds until we got a level that we were satisfied, and that was about an F1 score, about 70% for each of them. The final stage was what I call the final quality assurance. And of course, we could not review everything. That would become a manual coding from the scratch. So we needed to be smart and targeted revisions based on what we have learned during the process. So even we knew we would expect that some level of overprediction because we were prioritizing recall. So what we tried to do, we had a list of control checks, but one of the most important ones is that once we aggregated the classification across projects, we focused on the predictions that were unlikely or inconsistent or suspicious. So for instance, what would be a suspicion classification? A health project that was classified as investing in veterinary workforce, that would be weird. Or an agriculture project that was tagged as supporting medical countermeasure policies, that would be weird. So we identify all these suspicious or implausible sector intervention combinations and we review. We end up reviewing about 212 projects, that is about 2,500 chunk level predictions. And I'm glad that we did this because 75% of these suspicious cases were incorrect and we correct them. And in 25% of the cases, they were fine. For instance, we thought that an agriculture project would not have development of a vaccine. That was weird. Well, no, it was a vaccine for animals. So that makes sense. So it was correct. So this final step, also reinforce what we have been saying and how we designed the process. It was really a human in the loop exercise. AI generated the initial classifications, but we humans have the final judgment. So let me talk about a few lessons learned along the way. So as I mentioned earlier, one of the first lessons is that input text matter a lot. Should we classify entire document, section, paragraph, sentence, chunk? So each choice involves different trade-offs. If the text is too short, the model don't have enough context. and also increases processing times. This is what we observed. But at the same time, smaller text is easier from the human validation because you can clearly see where the text support the classification or not. If the text is too long, the model starts finding connections everywhere and increase the false positives. And this is something that I hear this week. I joined another glocal event from researchers from UCLA, and they mentioned the same thing. In their case, accuracy dropped with long documents, and they said like AI attention is beginning to drift. So they decided to do shorter chunks. A second lesson is that prompts are very sensitive. As I said, small wording have large effects in performance. This related to or described, it was important. And why? Because when you use the word related, it's like the model make a broader conceptual connection. So it would infer through an underlying theory of change that that text would deliver, would end up having an impact with the intervention he's classifying. And describe instead is much more literal. And this again was something that this another local event mentioned. In their experience, they said like AI was like reading between the lines and kind of what the text actually imply and not is strictly written. So those findings from this other event really resonate with our experience. The third lesson is, I would say, we need to be cautious with the AI-generated explanations. So we ask AI to provide one line of explanatory text, and it is good because it can explain its decisions. But some of those explanations were not very useful. Sometimes it could increase transparency, and it may help when you have a human reviewer that is less familiar with the topic. But occasionally, that explanation contains some reasoning that was not grounded in the text source. So even though the explanation itself sounds very convincing, but it was incorrect. So my lesson here is not to use explanations as validations. They don't substitute your validation, but we use it. It was useful to learn how the model thinks, and maybe it was useful for us to understand and make corrections and refinements. And the fourth lesson is more personal, maybe more speculative, and it concerns learning. This is my observation from this experience. And traditionally, when we do manual coding, many of us have done it. It is tedious, repetitive, but it also serves another purpose. And it is one way in which we evaluators learn about a new topic, because we spend days reading documents and we gradually develop an understanding of the interventions. The language that is used in different sectors, some sort of patterns across projects. So because of enough repetition, we start knowing the portfolio. And we may not realize it, but this is how we build like expert matter expertise at the same time. So when AI perform most of the classification and validation is absent or is minimized, this learning does not occur. So of course, AI creates other opportunities for learning. We learn to, prompt engineering, data pipelines, validation methods, but it may simultaneously reduce these opportunities to learn the substance content of the evaluation itself, in this case, pandemic preparedness. I don't know. I don't have an answer for this. What we gain with AI and what we might lose. but this was one of my observations. Let me just close with a final reflection here. So through this process, we experience that AI can dramatically expand what evaluators are able to analyze. It's increasing scale, speed, and consistency, but rigor doesn't come from the model. Rigor comes from the validation process that is embedded in the model. In this example, we experience that human judgment remains essential in defining the taxonomy, in selecting the input text, in validating the performance, in refining the prompts, designing the quality assurance test at the end, and ensuring that the evidence is credible. That is our job. So when we talk about quality in evaluation, let's make sure it is not a buzzword. Let's mean it. Because in the end, AI can assist in the analysis, but the accountability for the findings remain human. Thank you. Back to you, Joanna.
Thank you so much, Mercedes, for that deep analysis. And now we will turn over to Virginia for her presentation.
Thank you very much, Johanna, and thank you to all the attendees for joining in this session. So we have probably seen a lot of headlines like this on the news focusing on issues such as hallucinations, job displacements, biases in chatbots, etc. And these are, of course, very important considerations, and they can be incredibly useful to continue doing studies and research around all these topics, but they do provide a very LLM-centric view of AI risk. So in this session of this presentation, we wanted to shift gears a bit and move from the world of text that we've been discussing before to the world of images, and discuss how we can validate more rigorously different outputs produced by geospatial artificial intelligence results. So let's start by at the very beginning, but just giving a brief overview of what is geospatial intelligence for those that have a slightly different background. So as you can see on this slide here, so on the right-hand side of the slide, we have geospatial inputs. In this case, they're satellite images, but it could be any sort of georeference data. On the middle, you have a model, a quite complex one in this case, which is a deep learning approach that will take the input images, do some calculations on that, and produce some outputs. The outputs is what you can see on the left side of the image. And in this case, are land cover classifications, such as cropland, agriculture, snow, and so forth. So essentially, any geospatial model will learn to transform raw images into some structured information that can be used for different type of analysis. One point that it's important to highlight is that this is not purely experimental, but this type of analysis are already being embedded across evaluation workflows. So I wanted to illustrate some examples of these taken from recent IEG evaluations. And the way GeoAI typically enters the evaluation framework can be either through AI modeling techniques or through AI-generated data sets. This first example that you see here on the slide is an example of using an AI modeling technique, which is called semantic segmentation. In this case, so what we're trying to understand were some urban quality indicators in the city of Tirana in Albania. And the data set that we use were street view images. So for those of you that are not familiar, these are simply digital photos taken with either smartphones or digital cameras of the area of interest. And you can see on the slide 3 examples of these images. And what we applied is a model that's called semantic segmentation. which essentially what it does is map every pixel in the image to a specific class, which are the images you see on the bottom. So this in a way greatly simplifies the information that the image contains, but because of that, it also allows us to analyze it and detect different patterns. So for example, on the segmentation mask, you see that all the sky has been colored blue, the streets are gray, and so forth. So in this case, so we use approximately 10,000 images, all from the same city. And we used a grid overlaid over the whole city in order to make sure that we have enough coverage of different parts of the city. Given that these images have metadata, so and that includes the coordinates, so the latitude and longitude, so we can tell to which specific point these images belong. And we can use the metadata as well to filter images that are relevant for the analysis. In our case, we were looking at greenery. So for example, the season in which the images were taken is critical to ensure consistent results. So in this case, after applying this semantic segmentation model, over 10,000 of images, as I mentioned, so we were able to estimate greenness as an urban indicator, which essentially this means the percentage of green pixels over the percentage of total pixels. And we created that greenness distribution map that you can see on the slide. A second example that I wanted to mention is now switching to the use of AI-generated datasets. And in this case, we use a dataset of building footprints that created by Microsoft Bing that uses different computer vision algorithms to extract the outline of different parcels from a very large set of both satellite and aerial images. So the way we actually use this data set in an evaluation was on a very specific area of analysis, which was around the bus rapid transit system in Dar es Salaam in Tanzania. And we use this data set, which is what you can see it cropped to our area of interest in the first image on the slide. We calculated 5 different morphology metrics using a grid as well, mapping each building to a cell in the grid using the centroid of that building and performing the calculation for the metrics. I'm not going to go here into all the details of the calculations, but the intuition is that the shape and the size of the parcels can give a lot of insight into the different type of land uses. For example, informal settlements are typically characterized for smaller parcels that are more irregular in shape. So all these elements of the morphology of the parcels can be very indicative of the type of land use. So after we derive these different metrics, which are the 5 colored illustration that you see there, we were able to use a cluster algorithm to actually classify all these different type of land uses into a map that you see on the right side of the screen, which shows different land uses types around the BRT area, which we then validated closely working with local experts. And a last example I wanted to share with you, and this is also another example of using AI-generated data sets in the context of an evaluation, is the use of the Dynamic World data set, which is produced by Google. And this is an interesting case in that this data set produces almost near real-time land cover classes for Sentinel-2 images since 2015. And in this case, so we were working on a global biodiversity evaluation where we had over 500 protected areas that we were interested in, which would be prohibitively to do this analysis manually for all of these areas. So this dataset allows us to get a very preliminary understanding of the forestation and deforestation patterns across all of our areas of interest, which we then complemented with traditional data sources and methodologies to dig deeper into these patterns and try to understand better the situation in the ground. So as we have seen before, geospatial analysis can be used to derive evidence for evaluative purposes. However, there are many things that can go wrong in this process. And these models tend to have failure modes that are very difficult to detect. So in this part of the presentation, I wanted to share with you some of the specific considerations to keep in mind in order to make sure that the application is robust. One of the most important failure modes in AI, in the context of GeoAI specifically, is what's called domain shift. And so you can see here on the slides on the top row of the slide, you see images that all correspond to high income settings. On the bottom row of the slide, you see images that correspond to low income settings. And vertically, when you look at the columns, you see a comparison across different type of areas, so urban, rural, and informal settlements. So what you can see on the slide is how different when comparing high income and low income, the images look in terms of shapes, in terms of textures, and in terms of color. And this is not merely an aesthetic appreciation. It is very much related to how machine learning models understand the environment. And this is particularly applicable in the context of development applications. So many of the existing machine training models are using only high income setting images in order to build the training set, which means that when applied to a setting different from where it was trained, the models may still produce a result, but because the domain is completely different from the type of data where it was trained, the results are actually not correct at all and not informative at all. So this is a very important consideration to keep in mind. The second aspect that I wanted to mention is that geospatial artificial intelligence systems can reproduce different spatial and demographic biases. So on the example that we have here on the slide, which is taken from a paper that's referenced on the slide. So what you can see on the last of the 6 images is the ground truth. So these are images that show the segmentation of buildings on a very specific area also in Tanzania. And so on the last of the 6 photos, you can see the correct delineation of all the build parcels. The first 5 images show different models and their classification results. And what you will see if you look closely at the segmentation mask is how many of these buildings are being missed. The one that's most noteworthy is the 4th of the images, where you see that most of the buildings are actually not identified by the model. And the practical implications of this is that were this model to be used, for example, in the context of response to an emergency, the resources would not be distributed equitably, and many of the people in need of this sort of assistance might not be reached because they are not properly represented on this data set. The third consideration that I wanted to mention is that there's typically a trade-off between interpretability and prediction accuracy. And this is typical of many machine learning models, not only geospatial, but the pattern that's commonly present is that simpler models tend to be less accurate, but tend to be more highly interpretable. In contrast, more complex models tend to achieve a higher accuracy, but at the cost of reducing the interpretability of the results. And this is particularly true in the case of geospatial AI that sits at that top of high prediction accuracy and low interpretability. There are different ways and different algorithms that can be used in order to try to bring some understanding to how these models work. And so we can see on the slide an example of an algorithm that's called GradCam that essentially tries to highlight the areas of the image that mostly drive the activation of the model. So by this, I mean, and this was an example where we were trying to predict whether a certain area was urban or rural. So the areas highlighted mostly in red on these images are the specific areas of the image that the model thought were informative to make the decision towards the class being urban. These type of models can provide some level of interpretation. However, it is important to keep in mind that these are post hoc applications. They don't fully solve the opacity of the underlying model, but they can be a complement in order to get a better understanding of how the model derived its conclusions. Finally, I wanted to mention one more issue, one specifically applicable to geospatial artificial intelligence, and that is the issue of deepfake images or synthetic satellite images. So far, we have been assuming that the images we're working with are reliable. However, there's been so many advances recently in terms of generative AI approaches that it's becoming increasingly possible to create highly realistic satellite images. In the slide here, you can see 6 different images, and they all look quite plausible. They don't have any obvious artifacts. However, only 3 of them are real satellite images, and 3 of them are actually generated by artificial intelligence and don't represent any reality in the ground. So this also illustrates some of the other risks in terms of data provenance, and one of the considerations to keep in mind when working with this type of models. So with all these issues I mentioned before, so domain shift, the potential for biases, the existence of synthetic imagery, and the problems around interpretability and transparency in the results, I wanted to make a point towards a more rigorous validation system when using GeoAI models or GeoAI datasets. So one way to think about this is in terms of a layered validation approach, where each level addresses a different level of complexity or of potential issues that any of these models could have. So at the bottom of the pyramid, we can see here the most basic data validation model, which basically aims to address the question, is the model accurate? And in this case, so we're looking at different things. So that includes checking the data provenance, the correct labeling of the examples if using an approach that requires labeled data, as well as the basic technical validation of the model using different metrics, for example, accuracy or intersection over union in the case of images. However, this is the very basic validation and doesn't cover many of the other potential issues that could take place. A second level of validation would also look at the stability of the model. And this has to do with the issue of discrepancy between the training data and the data used for actually running the model for inference or prediction. So, for example, are the results stable under different conditions, such as different timeframes, different resolution in the images, different lighting conditions if looking at street view images. And this can also make a substantial difference on the results. The third level is looking more at the context and geographic validation. And here we're asking, is a model valid everywhere and for everyone? And by this, we mean, is the result of the model accurate in not in an abstract sense in terms of the technical validation of the model, but for the specific area that we are using in the analysis. As we mentioned earlier, so because of issues such as domain shift, it's possible that our area of interest is very different from the data used for training the model, in which case we still might get a good performance of the model in theory. But when looking at the alignment specifically for our area of interest, you will start to find a lot of discrepancies. It's also important to check whether the model performs well across different areas, even within our study area. So, for example, does it perform well both in urban areas and rural areas? And does it perform well for different socioeconomic groups? So, for example, higher income areas versus lower income. What typically happens is a model that performs well on average systematically underperform across some groups. And this is information that's important to gather in order to be convinced about the robustness of the analysis. And finally, the last layer is the decision validation. And here we're asking, is the model actually usable and trustworthy in practice? And so here we want to make sure is the model not only pass all our previous tests, but also is it used for purpose? In some cases, a model could be still accurate, but given the context in which it is applied, it might not be understandable because of all the transparency issues that we mentioned. So it might not be fit for purpose, or it might not meet the specific requirements for the local context. So, for example, is it being used in a sense that's consistent with the local application? So this is what we're trying to understand here by triangulating with different data sources, looking at the interpretability of the model, and comparing with expert judgment and domain knowledge experts. So to conclude this part of the presentation, I wanted to go back a bit to the beginning and to this example I showed you earlier on using street view photos to derive greenness indicators for Tirana. And I wanted to briefly show you how we actually applied this validation framework I just described to this one specific example. So at the very basic level, we knew where the images came from. So we were certain about the data provenance. We had extracted most of the images from a reliable platform, which is Mapillary, and complemented that with pictures that we took ourselves on the ground. So that wasn't an issue of concern in our case. But the model that we use already provides accuracy by class, which is informative on a general sense, but that says nothing about how well that applies to our specific context. So what we did in this case is we took a sample of about 15% of our images, and we segmented those images manually. So because of that, we can take those segmented images as ground truth, and we were able to do a comparison between our segmented images and those images segmented by the model in order to get a more specific accuracy for our specific area of interest. At the second level, we wanted to make sure that the model was performing well with the images that we were using for prediction. And so in this case, we used a stratified approach, and we checked for the accuracy of the model when looking at images having different viewing angles, different lighting conditions, and different resolution. And we did find, in fact, that the model was not performing accurately under some of these conditions, which led us to exclude some of the images from the analysis and rerun the model using those conditions where we were certain that the performance was solid. At the third level, we wanted to make sure that the way we predicted greenery actually matched with what's going on in the ground. And one easy way to do this is by using high-resolution satellite imagery. So with that, we were able to compare whether the masks that we obtained from the model actually corresponded across different parts of Tirana, which was actually being shown by these images. We also did a sample of some specific areas, and we worked with local consultants to actually go and manually verify those particular areas. And finally, at the very highest level on the decision validation, we consulted quite intensely with different urban planners and local experts, as well as triangulated with contextual studies in order to make sure that our interpretation of greenery and the importance of it as an indicator for urban quality match what was true in that particular location. So with that, I hope I was able to persuade you of the importance of rigorous validation on GeoAI applications and not staying only at the very bottom layer of the pyramid. And the key takeaways that I wanted to convey is first that GeoAI models can fail silently, unpredictable, and in ways that are very hard to detect. The second, that technical accuracy is insufficient for validation. And finally, that a human-in-the-loop approach is essential for trustworthy use. So with that, I'll thank you for your attention, and I'll send it back to you, Johanna.
Thank you very much, Virginia, for increasing our understanding of this complex approach. And we do have some resources available to you. These slides will be provided to you following the session along with the recording, but we have some resources for your consideration. And please do post your questions and comments in chat at any time. We do have a couple of questions that Mercedes has been answering for us, and Xiao Zhao. And actually, we're going to turn to Xiao Zhao now. Xiao Zhao Peng is an evaluation analyst who's working with Mercedes and Virginia, and we have a question for her on what's the difference between an open source free AI model that one could install on a computer oneself and a paid one that you need to log into. So I'm wondering if you can share your insights on that question.
Yeah, I think it's just when we're working with the AI, for any kind of this kind of text classification or whatever, working with the, this type of work, there basically we have different options, right? One is you're using the website, which is like the Claude, the ChatGPT, and then Google Gemini. So these are not free, right? It doesn't matter you're using either use the website or use the API to access the model. Literally, you have to pay for them, and then on the other hand, there's some free models you can actually download it to your local computer and run there. So that, but then there's a trade-off, right? The ones we're talking about, the paid ones, they tend to be more powerful, and also, you can access a lot, runs through a large, number of amount of a task through the API, which means you don't have to have a powerful computer. You need to have this memory, this kind of system requirement on your laptop or your computer. So that's kind of the efficiency, right? Of course, it comes with a cost. But meanwhile, when we're working with a local computer, yes, it is free, but it's more complicated to install the model on your computer, and you do involve a lot of, computer memory.
Thank you for sharing that perspective, Xiao Zhao. That's very helpful. And we do have a question in chat, Mercedes and Virginia, about other reports of the studies that you're referencing here.
So in our example, what we are using is project documents. They're not studies, project documents that here at the World Bank, they're called project appraisal documents. It is how the project is designed. So it's a document that has about like 60 pages. These are all publicly available, right? If you enter the World Bank website and you're interested in investments in a certain country, in a certain sector, you can find the projects, and these are accessible to the public. So these, as I was saying, these project appraisal documents have about 60 pages with annexes, and they have a typical structure. And we know that. We have reviewed many of them. So it starts talking about the background of the sector, of the country, and then some sectoral issues. And then it says these are the objectives of the project. So for instance, this investment is to improve the quality and utilization of health services in primary health care. And then it has a section that is called component, that is what we use in our case, in which it describes all the activities that the project is about to do in a 5-year period, right? So that component section, it varies, but it could be from 2 pages to 5 pages. It depends. That is the main text that we have used. We use titles, project titles, the name, that tells a lot, the objectives, and the component text. But the component text, as I said, imagine that you have like 5 pages. If you put 5 pages in the AI, it's a lot. Also, if you upload the whole project, then they have like institutional arrangement and other considerations in which you are not interested in the sense that if we want to classify interventions, which is what are the activities of the project, you are not interested in the background context. And that actually could be misleading, because if you insert that text, they may refer to, for instance, in the past, another project, this A, B, and C, and that is not what this project is doing. That is a reference from a previous project. So that is why the section of the document or the input text that you're using is so relevant. You need to know where it is more likely that you're going to find what you want. So I hope that answered the question. Is project appraisal documents. Thank you.
I can add
Mercedes.
a few more things. It's basically the principle is, for your input text, first is the relevance, right? If you have a long document, like Mercedes said, pick the most relevant section if you can, because that only is not about accuracy only, it's also efficiency, because processing long document also takes way more time, right? So that's one thing. The other thing is in terms of even you got the most relevant section, and then if it's still too long, you want to divide it into the chunks, right? In terms of the size of the chunk, that really you have to do some like testing, but make sure it's not too little or is it too long. And also when you're creating the chunks, make sure you're also using the overlapping strategy. So for example, you have sentence 1, 2, 3, and then you start with 2, 3, 4. So make sure you don't have those like segments and then they don't overlap and then there's something missing. Yeah.
Thank you so much, Mercedes and Xiao. We have some good engagement in the chat. We have some good questions, and we're taking them one at a time in order. And Mercedes and Xiao, there's a question for you on how did you get the right text segmentation from the long documents, and how did you validate results?
Okay, so we started with what we knew. And we knew it was our experience with supervised machine learning. So at that time, with supervised machine learning, we use single sentences. So again, the text cannot be like keywords because it is not interpretable. In one sentence, you can have something. So we started in one sentence. That is why we had the whole portfolio segmented in sentences, the whole portfolio, the component text, right? Segmented in sentences. We could run keywords there, keyword searches, as I mentioned in the chat, and that allow us to select a sample of projects that was very relevant for surveillance. That was the part of the taxonomy that we were testing, for instance, at the beginning. We start testing the taxonomy in parts. First, all the surveillance categories, then all the laboratories categories, and so forth. because we were working in parallel, developing and testing. So we started with one sentence, but also Xiao said, well, this for AI is too little, not enough content. So we tried about 3 sentences, and it was like a moving target chunk. So it was like a central sentence plus one sentence before, one sentence after, and that repeated in the next one. So we don't have loose spaces. So, and that worked better. And then we also tried at the end, we had to run the final model at 8 sentences, which was not ideal for me, but we had to because of the processing times. So why? Because imagine that you have a lot of chunks of 3 sentences, which it worked quite well, and also for the human validator. So imagine that you have to validate an entry that is a paragraph like this. In a paragraph like this, 8 sentences or more, you can have so many interventions. So it is not easy to read and to validate. So you need to test and play with differences and calculate your metrics across different chunk lengths and see which one works better. And you stick with that one. And also processing times is another variable. So at the end of the day, if you cannot, what was it? I remember in August, our other analyst, he said okay, to run the whole model across the 50 interventions and all the projects, I need 21 days. And said, no, we don't have that time. So we need to start aggregating chunks.
Thank you, Mercedes, for that summary of the main elements. Xiaozhao, did you want to respond at all to that question as well?
I think I already covered. Basically, just pick the most relevant section of the text if you know from the document to avoid the noise, right? And then the second one is just you have to pick the chunk based on the particular classification you're doing, right?
Excellent. Thanks so much. And we have another question in chat. Follow-up question for you, Xiaozhao. So you mentioned overlapping text segments. How did you use the overlapping segments?
So basically, when we're talking about chunks, right? Let's say, assuming you have a document have 10 sentences, and then we're saying, okay, we divided to, 5 chunks, but then we're not doing sentence like 1, 2, and then 3, 4, and then, 5, 6, right? Because that's not going to work. Because what happened is maybe sentence 2 and 3 are talking about same thing. If you just literally divide them into, sections, that means information will be missing. So what we're doing is sentence 1 and 2 is a chunk, and then overlapping 2 and 3 is a chunk, and 3 and 4 is chunk. So make sure all the sentences are connected to each other in the chunks, not just literally divide them into, separate segments. So that's the idea. So make sure all the sentences can be linked to other so people can read it in the context, not just single sentence.
Thank you, Xiaozhao, for covering the key factors to consider. And I have a question for Mercedes and Virginia, and that is, what kind of resources did this AI application require? So who was on the team? What roles did they play? How much time did it take to implement?
You can go ahead, Virginia.
Thank you. So in our case, there were different applications on Chio AI, but the composition of the team is always essentially the same. So there's always a geospatial specialist, a remote sensing, computer vision that can actually run the models, suggest on the best methodological approach, and be aware of all the limitations. There's always the evaluation team, of course, and this is always done in very close coordination with the evaluators in order to make sure that the analysis will eventually be useful to answer a specific evaluation question. And the third big piece is the subject expert in the topic that we're looking into. So for example, for biodiversity, we have an expert on forestation because we were looking at terrestrial protected areas. On the Tirana case, we had an urban specialist that acted as domain expert and so forth. But I think those are the 3 key pillars in terms of composition. In terms of timeline, it probably took us about 3-4 months total in order to develop these applications. Obviously, it varies a bit for each of these. But this includes basically the very initial stage in terms of conceptualizing the analysis to the actual application of the model, and including a quite extensive phase at the end for validation and refinement and rerunning the model if need be at that stage.
And Mercedes, over to you.
Yes, and in our case, last year in April, we started just Xiao and myself. Xiao is the data analyst, and I am the health economist leading this evaluation, and in particular this analysis of portfolio review. And then later we had a new analyst in the team. When we switched to GPT-4 and so forth, I mean, he took the lead on the analysis there. And in terms of roles, for instance, in this 5 stage that I was mentioning, I mean, we work together all the time. I mean, we have to say that it's important. I mean, close coordination, close work with your analyst. And I was more in charge of the development of the taxonomy and the design of this roadmap and validation process. And Xiao was collecting the data, cleaning the data, and also starting with the first the models and the prompt, and then it came back to me, the sample, and I do the human validation quite a lot across 6 out of the 9 themes. I did it myself, so a lot of manual coding. That is how I learned what the bank is doing in pandemic preparedness, which is good. And in terms of timelines, we started in April. We kind of finalized by September. So it took us some time. This was the first experience that we had with AI systematically for classification. Now it's not the only one, but it was the first. And we learned a lot, and we find that now it's more easy to apply to other evaluation tasks. So this one was hard because we were not sufficiently trusting AI. And I think that developing a validation framework is so important to build credible results. And so we evaluators are confident and comfortable with the findings that we're showing. Thanks.
Excellent. Thanks for providing those key considerations, Mercedes and Virginia. I'm going to have a couple more questions for you. And looking in the chat, nothing at the moment, but for Virginia, do you do the same validation and transparency challenges apply to foundation models and satellite embeddings?
Yes, thank you for the question. And yes, lately there's been quite a big push towards more foundational models, and these come with their own risk. And in a way, I would say that the issues I described apply even more to foundational models and satellite embeddings, especially 2 of them. One in terms of domain shift. So these are very large models that are typically built with a specific data set. So for example, Sentinel data or Landsat data for specific periods. So whether that data set used for creating the embeddings or the foundational models are the same that the data used for inference, that still remains a big question. And the second is on the opacity. And because again, the very large size of these models implies that they are intractable, in that it is impossible to, as a human, to recalculate everything to see how these embeddings were produced. So it raises the question of whether, we are implicitly trusting that model. without the possibility to open in the black box in a way to see what's the inner working of it. So I think it's there. I'm not saying with this that it shouldn't be used. That's not the message I want to say, but that we need to be careful as evaluators in terms of the validation we applied to these models as well. Thank you.
Excellent. Thanks so much, Virginia, for that perspective. And just we'll take one more question, and we'll also watch the chat and see if you have any other questions for Mercedes, Virginia, and Xiao Xiao. So this question's for Xiao Xiao. Do I need to code? So can you do this work in ChatGPT or Claude without writing any code?
Yeah, so basically this really depends on, the text size you're trying to process, right? Let's say we have this, too many projects, we cannot really using the chatbot just uploading thousands of project documents and then run analysis because that's impossible. But meanwhile, think about if you only have, 20 documents or 30 documents, that's definitely doable in the chat, in the chatbot window, like online chatting, uploading your document. But what is most important is the prompt. It doesn't matter you do it with the coding or you do it online. You make sure your prompt is good. That's the basic for the quality assurance.
Excellent.
Johanna, I see a question in the chat that may have been
Please.
skipped. Can I read it?
Absolutely.
It is from Dana.
Absolutely.
It says, what was the expected output of the revision of these appraisal documents using AI? What did you want to produce? Sorry if I miss it. Yeah, so this was the beginning of the presentation. We were doing an evaluation. I say were because we are finalizing it, so it may be published after the summer. So this was to evaluate the World Bank support to pandemic preparedness. It's a thematic big evaluation that covered 25 years. When we did the portfolio identification on what are the projects that are relevant to pandemic preparedness, we found 1,300, quite a lot. So one of our evaluation questions was whether the bank support was relevant, whether it was relevant to address the country needs in terms of preparedness capacities. So we had external data on that from countries using international health regulations. So a basic portfolio review always had to provide, okay, what this World Bank support look like? What were the objectives? What were the interventions? So that is why we had to develop a taxonomy of interventions to code and classify this project and be able to say, well, most of the preparedness supports of the World Bank lies within food safety investments and not so much in wildlife animal management, for instance. Was it to prepare a new appraisal document? No, we use appraisal documents because these are the description of what the project is aiming to do. At the end of the project cycle, after the 5 years, when the project closes, then we have another document, which is called implementation completion report, where it says, okay, this project did this and that, and they achieved these results. So some of the portfolio, generally about 60% of the portfolio, are still active projects. And then you have a share of projects that have been closed. So you can learn about effectiveness, but you learn about effectiveness if the project was closed. You cannot learn about effectiveness if the project is still active. We will have to wait until it finished. Thank you.
Thank you for that excellent explanation, Mercedes. And I'm going to move to Virginia just for one more question for you. How can evaluators work with GeoAI systems if they're not technical AI remote sensing specialists?
Yeah, thank you for the question. The critical part is I think the collaboration between the geospatial specialists and the evaluators. the evaluator doesn't need to know all the technical details or be able to implement all these different aspects. But I think it is important for evaluators to be aware of what the possibilities are, but also what the failure modes can be, to be on the lookout for these particular problems. And we normally work in close collaboration with evaluation teams, and also because we want to make sure that the analysis is not just a theoretical application, but something that helps actually answer an evaluation question. So there is always a very close interaction throughout the process. Thank you.
Excellent. Thank you, Virginia. Xiao Xiao, did you want to chime in on that question? I thought you might have your hand up.
Yeah, no, I think Virginia has mentioned pretty well. Yeah, that's
Perfect.
Yeah.
Excellent. Well, I think we will wrap up at this point, and thank you very, very much for joining us today, for your questions and comments. And thank you very much to our speakers, Virginia, Mercedes, and Xiao Xiao. And just to quickly summarize our experience, what we talked about how you can expand what evaluators can analyze, the importance of rigor coming from the evaluation, from the validation embedded in the model, and that human judgment is essential. I think that through the examples provided today, we've seen the importance of rigorous validation and responsible use for acquiring stronger validation frameworks. And so thank you very much. I hope that you have learned something today that you can apply in your work, and we look forward to engaging with you again in the future. Thanks so much. Bye, everyone.
Thank you.
Thank you.
Thank you.